Hey, let's go look at arc length here. This is topic 8.13 in the official AP Calculus course of study. I don't know if that matters to you. And in this lesson, I will only be looking at arc length in the context of rectangular graphs, Cartesian graphs, just your good old XY plane. There is arc length in polar and parametric equations as well, but I am not going to look at those. If you need to print the sheet that I'm going to use for notes on this, you can go to this bit.ly link right here. So let's get into arc length. And the first part of arc length is going to shock you, but the purpose of arc length is to find the length of a curve. So the object is to find the length of a curve or graph if you were to take a graph, stretch it out, and maybe put it on the x-axis to measure its length. And what I'm going to do right here with this little diagram, and I have some little lines drawn in there, is to show you how we're going to generate the formula, and ultimately it's an antiderivative that finds the length of a curve from point A to point B. And what you can see that I've done so far is I've taken this curve, and if my object is if I want to find the length of it, I could get an approximation for the length by dividing that curve up into a few pieces and using the distance formula. I could find the length of all of these little zigzag lines connecting different points on the graph. And the sum of those lengths would be an approximation for the length of this curve. If I want the approximation to be a little bit more accurate, then kind of like with Riemann sums, you take more subdivisions. And so if I divide this up and decide to do the distance between these points that I've drawn, now you can see that if I add all of these green distances, they start to hug the curve a little more closely. And all of those distances add together will be a more accurate approximation for the length of the curve. And so it won't be a surprise, hopefully, when we get to the final formula that the answer will resemble the distance formula. And before we get into that, we need to remember what the distance formula is. The distance formula is nothing more than the Pythagorean theorem with a coat on it. So there's what you should have learned many years ago. And you can call the x2 minus x1 and y2 minus y1 your change in x. So you could rewrite that as delta x squared plus delta y squared all under the radical. And what I am doing is I'm taking a whole bunch of these, and I'm just saying I'm just going to declare let's let n equal the number of subdivisions, just like Riemann sums. Subdivisions. And if n is the number of subdivisions, what I'm going to do is I'm going to find all of those different lengths and I'm going to add them together. I'm going to find the sum of those. And as long as n is finite, that will be an approximation. However, if I want this to become the exact distance, the exact length of the curve, then I will take that summation and I will see what happens as n goes to infinity. What if I take an infinite number of subdivisions? And what will happen is the same thing that happened with Riemann sums. That little summation symbol, the Greek letter S, turns into this elongated S, and the delta x and the delta y will be replaced with dx and dy. And so this right here is essentially what we're going to end up doing, except having dx and dy in an antiderivative can be a little bit tricky, especially if you are familiar with only the Cartesian rectangular coordinate system in the context of calculus. So what we're going to do with that is we're going to tweak that formula, the square root of dx squared plus dy squared, so that it becomes something that we can work with. And I'm going to do just a little bit of algebra with it. And I'm going to start by dividing both the dx squared and the dy squared by dx squared. And divide both of those by dx squared. Well, if I divide them by dx squared, I have now altered the formula. Pray I don't alter it further. Well, I actually need to alter it further because I have to undo what I just created. If I divided by dx squared, I need to multiply each of those by a dx squared. And I'm going to do that by sticking a dx squared out here. I could put that over 1 if you want to. So I have multiplied by dx squared and I have divided by dx squared. This dx squared right here, because that is under a square root, that dx squared can come out as a single dx because the square root of dx squared would be dx. And then dx squared over dx squared, well, that's just going to equal 1. And dy squared over dx squared would be the quantity of dy dx squared. And so I'm going to take that and I tweak it into this formula. Now it looks maybe a little bit more familiar, more like an antiderivative. It's the integral from a to b of the square root of 1 plus dy dx all squared dx. And the last little tweak I'm going to make before you see the official formula for arc length is that I will change dy dx into f prime of x squared. And that is the formula we will be using for arc length. A lot of people are very comfortable just memorizing the formula and having no clue where it comes from. However, I do believe there's value in seeing the origins of certain formulas, especially when it's fairly straightforward. And I don't know if that was straightforward to you. But some proofs in calculus are extremely complicated and not worth the time, in my opinion. This is not one of them. So let's go on and put this into practice after we write this down. So arc length formulas, do keep in mind we are not looking at polar and parametric curves yet. I will do that with my students later. And if you need to see it now, then you'll have to look up another video to get the polar and parametric tweak of these. And so we can find arc lengths of two different types of functions. The traditional one is y equals a function of x, and that is exactly what we were just looking at. And so that is the exact same formula we just wrote down, 1 plus f prime of x squared. We also may have functions that are written in terms of y. So if x is a function of y, it's the exact same formula, exact same integral from a to b of 1 plus the derivative squared. We just have it as the derivative of y squared, and in that case, it would be a dy antiderivative, not a dx antiderivative. And one thing to keep in mind is that these problems do typically create very difficult antiderivatives. You can create a function so that when the derivative is plugged into this formula, it gives you something that's kind of manageable and fairly nice in arc length, but it's very common for these to be very difficult or impossible to evaluate by hand in the world of elementary functions. And so if you are an AP calculus student, these are typically calculator problems where you'll set it up and then throw it in a calculator, or it will be a situation where you are asked to set up the antiderivative but not evaluate it. So let's look at a few examples. And this first one, we are asked to find the length of a curve, and the curve is the inverse tangent of 2x on this interval. And if I'm going to find the length of a curve, I need to find the derivative of that equation. And in this case, y prime, your derivative of inverse tangent is 1 over 1 plus its argument squared. So it'll be the quantity of 2x squared. But this will be a chain rule, so we need to multiply by 2. So we have a nice clean derivative of 2 over 1 plus. And if you want to square that, that would be the quantity of 4x squared. So find that derivative first. Then for the arc length, we will plug that into our arc length formula, which is the square root of 1 plus that derivative, 2 over 1 plus 4x squared squared dx. Make sure you include the limits of integration, 0 to 3. And this is a calculator active problem. It says you may use a calculator, so definitely write it down in great detail. Then we will write equals and we will write the answer. And I'm going to go to my calculator and get that and be back in just a second. And here's my answer. I got 3.583 if you want to follow standard rounding procedures, or you can truncate that to 3.582. And I say that as an AP Calculus teacher. If you're not in AP Calculus, then you'll have to ask your own teacher or professor how they prefer you to present your answers. And I did use the TI Inspire to get my answer. So there you can see the calculator screenshot. Let's go on to number 2. Find the length of that curve on this interval. And again, we're from 0 to 3. This time it's a function of y, not a function of x, but that's no big deal. So this time I'll actually find dx dy, the derivative of x with respect to x, with respect to y. And it's a square root function. So the derivative of square root of stuff is 1 over 2 root stuff. And that, again, is a chain rule. So I need to multiply by the derivative of the inside. So that's negative 2y. And that will clean up ever so slightly. You can divide those 2's out to be left with negative 1y in the numerator over the square root of 36 minus y squared. And then we will throw that into the antiderivative for arc length. The length will be the antiderivative from 0 to 3 of the square root of 1 plus my derivative, which is negative y over the square root of 36 minus y squared squared 1 plus y prime squared x prime squared dy is, and again, we will go to the calculator and throw this in and write down the answer. Okay, and I ended up getting, for my answer, 2.549, and that is the truncated version. So here's the screenshot of what I entered in my calculator, and I just now realized I made a mistake. So you have to be very careful when you punch these in. I'm looking at this, and I forgot to square the derivative, so I'm going to have to pause this and go back and fix my answer. So be extra careful with your calculator usage and make sure you get everything put in correctly. So hang on just a second. Actually, I'm going to show you really quick how I edit this because some people are not as proficient on the TI Inspire. So I'm going to go off on a little TI Inspire tutorial. I need to go back and edit this, and I really just want to square that little piece. So instead of entering the whole thing from scratch, if you arrow up, so I'm going to hit the arrow up button. And when that is highlighted, if I press enter, it will bring it down to an editable screen. And I'm going to show you another trick. If you hold down your shift button, and I'm using my keyboard, but this works on the calculator as well. If you hold down shift and arrow over, it will then selectively highlight stuff. I'm going to put that in parentheses. And now I will put an exponent of 2 right here. Hit Control Enter to force the decimal, but I feel like I would get a decimal anyway. And 3.14159. Boy, isn't that a familiar number? And so here's the answer, 3.142, 3.141. And the reason we got pi, if you were thinking, this is the graph of a semicircle. And I randomly chose the interval 0 to 3, and I guess I just happened to choose the correct one so that we ended up with an answer of 1 pi. So the answer would be a multiple of pi because we are talking about the piece of a circle. Just a little interesting thing that happened right there. So on to the last problem, which is actually 3 problems in one. So I have a region R shown to the right, and that is the graph of, well, you see the equation, x cubed over 3 minus x plus 2. And we're in the first quadrant bounded by the axes and x equals 2. And this is designed to be more of like an AP style question with multiple parts based on the same prompt. And the first question is not an arc length question, so I'm going to go over this one very quickly. It's an area question. Fairly straightforward. Area between the curve and the x-axis is the antiderivative of the curve from 0 to 2. And I went ahead and typed all this out. So if you want to practice this and not see the answer, then pause the video because in about 2 seconds, I will reveal the answer. 1, 2, and there is the rest of the answer. In the world of AP Calculus, you would stop right here, please. Please do not evaluate or clean up answers in multiple choice world, or if you have a teacher who just prefers you to simplify your free response answers, you would need to go down to 10/3. So let's look at part B, same region, and we are rotating this region around the x-axis. And again, this is not an arc length question, so I'm going to go over it kind of quickly. If you rotate that around the x-axis, it's a disk. That is going to be a dx problem. The area of a disk is pi r squared, and the radius of that disk is going to be the distance between the curve and the x-axis, which would just be that function, which I'll declare to be f of x. So r is just the f of x equation. So we'll do the antiderivative of pi r squared. And again, I'm going to just show the answer. If you want to set it up and practice it on your own, you can. And here is the answer. This one did ask you to set up, but not evaluate. And the reason I wouldn't want to evaluate this is because the only way to do that antiderivative without a calculator would be to expand that completely. And so that brings us to question C. And this is what I'm going to do in a little bit more detail. Find the perimeter of the region. Now, perimeter means we need to add up every side that is bounding this region. 3 of the 4 sides are going to be pretty nice because this side right here is just a length of 2. This side right here is a length of 2. This side is going to be, well, whatever that y coordinate is. I know the x coordinate is 2, but I need to find f of 2, which is not going to be too bad because 2 cubed over 3, that would be 8/3. And then minus 2 plus 2 would be 0. So that side length over there is 8/3. And so I know the perimeter is going to be 2 plus 2 plus 8/3. But the tricky part is going to be getting the length of this piece, and that's where arc length is going to come in. So to get that length right here, which we're going to have to set up that antiderivative formula, the antiderivative from a to b, we're going from 0 to 2 of the square root of 1 plus the derivative of your y, your equation, so y prime is going to be, this is kind of nice, the derivative of x cubed over 3 is just x squared. Derivative of negative x is negative 1. So it ended up being kind of nice. X squared minus 1 squared dx. And when you put this in the calculator, just be careful that you don't forget about the 2, and the 8/3. Some people focus so much on the antiderivative side of this that they will forget to include the other two pieces. So I'm going to punch that in the calculator very quickly, and you'll see the answer in a second. And there is my screenshot of my calculator entry, and I'm getting, I did put that in correctly. Yes, I did. I got 9.657 for the perimeter. So there is a introduction to a lesson on arc length in the Cartesian system, and we will do the more complicated polars and parametrics later.